I will begin with a word of prayer. Here we go. Heavenly Father, we thank you for this day. I thank you again for these students, and I just pray that you be with us today. Help us to glorify you in what we do, and I just pray we'd understand your creation a little bit more deeply together this day, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me just say a little bit more about inertial coordinates. I had this sense last class that there was something I was saying that wasn't quite right, and I'm not sure I said anything wrong last class, but there's something left out. So let me just kind of revisit a bit. So inertial coordinates. So in your homework problem, like problem 20, for example, I use this like big X, big Y notation. So let me just lay down something here. So x1, x2, x3, this is the coordinate system X. And let Y be, say, y1, y2, y3, coordinate system Y. All right? Then here's the definition. X and Y are naively inertially related. Inertially related. All right, if there exists constant vectors r sub 0 and v sub 0 for which y is equal to x plus r sub 0 plus t times v sub 0. All right. Now, I think I might have said this last time. Well, at least I implied it, perhaps. This is not, it's not wrong to say that if this is the case, they're inertially related, but technically speaking, the concept of inertially related coordinate systems in classical mechanics, it's a little bit more nuanced than this, because you're actually allowed to insert a rotation matrix here, a fixed rotation matrix. Like, for example, if I take the system of coordinates based in the corner of this room, right, and I just take that system of coordinates and I rotate 45 degrees, like that, all right? And I'm not saying in a timely sense, I'm just saying once and for all, rotate the coordinates so that you've got rotated coordinate systems like that, right? There's a fixed rotation matrix that will take you from the original system of coordinates to the rotated one. Those coordinates are also said to be inertially related. But I'm not allowed to talk about those in here. Why? Because linear algebra is not a prerequisite for this course, right? So you don't know what a rotation matrix is. We can't. Do you remember studying rotations in Calculus 1 with analytic geometry, right? Yeah, with analytic geometry, but not that geometry, right? So you guys don't know about rotations, unfortunately, so I can't do what's actually the truth, which is to put an R here for rotation matrix. That is actually generally what we would mean by inertially related coordinates, all right? So since we don't have that, I have to keep it a little bit simpler, and we just say that this constitutes inertially related coordinate systems, okay? And if that's the case, so if this is the relation between the position vector in y and the position vector in x, then you can differentiate this, and it gives you the velocity in the y system is equal to the velocity in the x system plus, well, v naught, right? And I probably should put a vector on these. And then if I differentiate again, I get the acceleration in the y system is equal to the acceleration in the x system, right? So if two coordinate systems are inertially related, and you study the motion of a physical body, what has to be true for both? If we're talking about unrotated coordinate systems, okay, then it must be the case that the accelerations are equal. All right? So, for example, if you have Bob, and Bob has, on the one hand, Bob has, in terms of the x coordinate system, t t cubed plus 1 and 2t. So that's his x coordinates. All right. And in the y coordinate system, we measure Bob, and Bob says Bob has position 2t minus 1, t plus t cubed, and 7. All right. So I want you guys to work it out for yourself. What is the velocity in the x coordinate system? What's the velocity in the y coordinate system? What's the acceleration in the x coordinate system? What's the acceleration of Bob in the y coordinate system? Work these out, and you guys tell me what we should get for these 4 vectors. And then once you do that, tell me whether or not it's possible that x and y are inertially related coordinate systems. So by the time I walk back to the back door and close it and get back to the board, you should have done these differentiations. They're not complicated. All right, what do we got here? 1, 3t squared, 2. With respect to the y coordinate system, we've got 2. 1 plus 3t squared, 0. Acceleration in the x, 0. 6t, 0. Acceleration in the y, 0. 6t, 0. So logically, what's the conclusion then? Yes, the accelerations match. The acceleration of Bob as measured in the x-coordinate system matches the acceleration of Bob as measured in the y-coordinate system. So it's possible that these are inertially related systems, right? It's possible. And if you wanted to, you could even figure out what v naught would be in this situation, right? Because if you look at this formula right here, if you take the difference of Vy and Vx, what do you get? You get V naught, right? And so you could actually figure out what the velocity of these 2 coordinate systems was with respect to each other by taking the difference of the velocity of Bob as measured in the one coordinate system versus the other. You know? You could figure that out. It wouldn't be hard. If you subtract y and x, you get what? 1. The 3t squareds cancel. 1. Let's see here. Minus 2. So V naught would apparently be this, right? And I suppose if you wanted to, you could even go back and figure out what R naught would have to be. I haven't done, I don't really care, all right? The point is, would this prove that they're inertially related? Well, no, right? It could just so happen that Bob has the same acceleration, right? But that's just a quirk of the way Bob is going through space, right? There might be some other path where you measure the acceleration with respect to the one frame versus the other, and you get a different acceleration, right? So conceptually, to prove they're inertially related, you'd have to test all possible paths and show that all possible paths have the same acceleration measured in both frames, right? Again, we're working with non-rotated frames because this is physics 231, right? So all I can really do for sure is if the acceleration of a path, of a particular motion of a body, a physical body, if it has a different acceleration with respect to one frame of reference and with respect to another, since we're not working with rotated frames, right? If those accelerations don't match, they're not inertially related coordinate systems. Yeah?
What does inertially related mean in a physical sense? Like, what's a manifestation?
This formula means that the coordinate system x and the coordinate system y, their motion is related by the constant velocity with respect to one another. That formula means that the origin of the x system moves at constant velocity in the y system and vice versa. So one way to look at all this is Newton's first law. What it really says is that there exists an inertial coordinate system out there somewhere, right? Once you have one, then you can find more by moving constant velocity motions with respect to that initial given frame. Logically speaking, people who want to think harder about this from a philosophical perspective, they say something like, well, the fixed reference frame is the one that's set up by the stars, right? They're out there, they're essentially immovable, so you could use the stars to set up your fixed reference frame, right? As we study astronomy more deeply, that's not quite right, because there's like a motion of the Milky Way galaxy through the larger galactic cluster or whatever. Don't ask me the specifics. Everything's moving, so, you know, whatever. Okay, I just wanted to say that to try to help you with that one homework problem, yeah? So, moving on here. Let me talk for a minute about friction. So, what is friction? So the force due to friction, right? The magnitude of it is mu. If we're talking about static friction, mu sub s times the normal force. So what's the normal force? Well, let me just try to explain this further. Example 2, I suppose. So you have a box with mu sub s equals to 0.5, all right? As pictured. So here's the box, all right? And let's give the mass of the box, let's say 20 kilograms, all right? And my choice of where to label the m was poor. Let me put it over here. M equals to 20 kilograms. All right, great. So what, and then let's also say that you've got Mr. Top Hat over here, and he's pushing on the box. He's pushing on the box with a force of, let's say, F sub naught. All right, he's pushing on the box. So you could think about the box as like this chair, right? Mr. Top Hat is pushing on the chair, right? And if you push on the chair and you don't push hard enough, what happens? It doesn't move, right? But there becomes a certain force where if you push hard enough, it starts moving, right? Now, once it starts moving, we're no longer talking about static friction, we're talking about kinetic friction. So it's a little bit complicated because the force of friction, if I'm not pushing on it at all, what's the force of friction? Force of friction, 0, right? And then I start pushing on it. I'm pushing harder and harder. I know you can't see it, but I am. And then at some point it starts to move, right? So I really shouldn't say equals this. To be more accurate, it's less than or equal to this. Because the maximum static force of friction is mu sub s times n. All right? So it's 0 all the way up to that. And so if I was going to graph the force of friction, it looks something like this. So you got 0, right? And once you get to, so here's the force of friction is this way, right? So you have all the way up to here, and this value is mu sub s times n. And then past that, it typically drops back down. And down here, you have mu sub k times n. That's the force of friction once you get past like a certain amount. So we could, so let's see here. This is the force applied, essentially, F naught. That's the graph that's going on here. I apply 0 force. It's not, the force of friction 0. I keep applying force, and the force of friction opposes my pushing on it up to the maximum amount, which is mu sub s times n, and then it drops back down to mu sub k once it's moving. And you'll experience this if you try to push a box across a room or something, right? It takes a little bit more to get it moving. Once it's moving, it's easier to keep moving, right? And if you stop moving, it takes more effort to start moving it again. Okay, so if mu sub s is 0.5 and mu sub k, so the kinetic coefficient of friction is typically smaller, so say 0.3, then let's analyze the situation here. Let's explain what happens, right? So what's the normal force, I guess, is the larger question here. What am I talking about, normal force? I never explained that in here yet, have I? Let's talk about it. So if the box is sitting on the plane, right, we can draw what's called a free body diagram on it. So essentially, look at the center of mass of the box, right? And you've got the normal force goes upward. The normal force is the force that the surface which the box is sitting on pushes up on the box, all right? Why is the surface pushing up on the box? Well, there's also, we're always, by default, these problems are on Earth, right? Close to the surface. And so by default downward, you've got mg, which is the force of gravity, right? F equals mg, like I mentioned last time, downward, yeah? So those are the vertical forces at play. Horizontally, I have the pushing force, right, F naught, like this. And where is the force of friction? So which way, where does the force of friction go? When I press on the box, is the force of friction, is it go in the same direction I'm pushing? Does the friction force push the box along with my pushing force? No, right? Exactly the opposite, right? So the friction force is always directed opposite the potential direction of motion or the actual direction of motion. So here, force of friction, I'll put it in this. Oh, wait a minute. No, this isn't okay blue. I thought it might have been. Oh, no, it's the hideous blue. Oh. Ugh. Sorry, Carolina. Force of friction is opposite. So, sorry, they are evil, though. But, okay, so what does Newton's second law say? The net force is what? Mass times the acceleration, right? What is the net force here? Symbolically, the net force, it's the minus mg y hat. It's the plus n y hat. It's the plus f0 x hat. It's the minus force of friction x hat. I'm assuming that the force of friction is taken to be positive. It's the magnitude, yeah? I put the directions in by hand, pluses and minuses. This is a vector, so two-dimensional. So we have two different equations here. We've got the horizontal and the vertical. So let me see here. I chose poorly. I should have written this over here. My bad. It's okay. So vertically, it's kind of boring. By the way, so before it starts moving, what's the acceleration? It's 0, right? It's in equilibrium before it starts moving. So at that stage, we just have 0. Well, let's see here. We have minus mg plus n equals to 0. So in this special case, the normal force is equal to mg. So that ain't bad, right? Now, what about horizontally? Horizontally, what's going on? We've got the force of friction, and we've got F naught. So we've got F naught minus the force of friction equals to 0. When it's in the case of static, right, before it's moving. And so what is the equation here? So apparently, we have that the force we're pushing on, the force of friction, right, has to be equal to what? A couple different things. On the one hand, it's equal to, by definition, so the force of friction has to be equal to F0 if it's going to stay in equilibrium, right? But what else do we say? It's less than or equal to mu sub s times, less than or equal to what? Less than or equal to mu sub s times n, but what is n here? Mg, right? So what does this say? This says, let me put the numbers in, yeah? So this works out to what? 0.5 times, what did I say, 20 kilograms times 9.8 meters per second squared. So what's that work out to? This number is, it turns out it was, I'm the one who lost my calculator. I was blaming my kids, but it was me all along. Oh man, did I leave it in my office? Come on. Seriously? Oh, I'm the worst. Oh, wait a minute, here it is. Let's see here, 0.5 times 20 times 9.8. All right, so the maximum available force of static friction is 98 newtons. 98 newtons, that's all you get. So in this hypothetical box, if I push with a force of less than 98 newtons, it doesn't move. It's in static equilibrium. What happens when I suppose I apply 100 newtons, then what happens? So this was case 2. So this was case 1 up here. Static. Case 2, apply 100 newtons. Well, now the situation's changed, right? We've overcome the force of friction. Now the box is moving. We're in the kinetic regime. So still, we have the normal force is equal to mg, right? But once it's moving, the force of friction is not variable anymore. It's a constant, right? But the force of friction now is equal to mu sub k times n, which in this case is 0.3, because I told you it was, times the normal force, which was mg, right? 20 kilograms times 9.8, yeah? And what does that give us? Thank you, 58.8 newtons. All right. Now let me erase this funny business over here. If I can find my beloved eraser shirt. Here it is. All right, so things are getting too crowded on that one board. Let's let me just draw the free body diagram for the situation in motion, right? So moving. All right, so here's my box. I've got my F sub 0. I told you it's 100 newtons, right? I've got my force of friction this way, right? And what did we say it was? It was equal to 58.8 newtons once it's moving. By the way, my apologies for the notation here. It's not ideal, right? Because here, N is a meter, good grief, a meter kilogram per second squared, right? Mass times acceleration. The units of acceleration, meter per second squared. Mass is kilograms. So this is what a newton is. A newton is a meter kilogram per second squared. Not to be confused with the normal force. All right. Sorry. This is the notation. All right. It's usually clear from the context which is meant, but now that's the horizontal, but of course vertically what's happening? You still got your normal force like this, and you got your mg like that, right? So this is called a free body diagram. What we do is we draw all the different forces on the object to understand what the net force is, okay? Now the net force here is not 0, is it? What's the net force? So the y, I mean, I'll write it in the bracket notation, okay? So it's 0 over here, right? The net force in the vertical direction is 0, but the net force in the horizontal direction is what? It's 100 newtons minus what? 58.8. So the net force is actually, what is it? What's that? 41.2 newtons, comma 0, right? So what's the acceleration of the box? Remember, F net is equal to what? Mass times acceleration. So to find the acceleration, I take the net force, I divide by my mass, which in this case I told you was 20 kilograms. And what's that give us? You guys tell me? 2.06 meters per second squared, comma 0. Now, does it make sense that the acceleration in the vertical direction is 0? Do you understand why that should be? What would it mean if the acceleration of the box in the vertical direction was positive? It would be just flying up off the table, right? If it was negative, it would be going into the table, just like the vertical acceleration of this chair is 0, right? It's not flying up. It's not going into floor 3, which would be kind of a little bit disconcerting for the people down there, right? But we can give it horizontal acceleration, right? And then, okay, so then you can go from here and answer all kinds of questions, right? Like, if you apply 100 newtons to the box initially at rest, how far does it move after, so much time, right? Then you can go and use the constant acceleration formulas. See, because this is a constant acceleration. So then all that kinematic stuff we just learned still applies here. All right? So this is how friction works. Now, you have to pay attention. It's the normal force that determines the force of friction. So if there are other vertical forces on the box, the normal force doesn't have to just match gravity. If I'm pushing down on the box, I can increase the normal force. Because if I push down with the weight of the chair on the chair, there's twice the weight of the chair on the floor. So the normal force would be twice mg. You have to think through it for a given problem. You can't just assume that the normal force is always equal to mg. That is, in this special case, the case. Yeah. Yes, sir?
If you are pushing down on it, would that change the friction constant?
No, the friction constant is a material characteristic of one object and another. It actually is, it's a macroscopic consequence of the materials that are interfacing. So it's actually different for the chair on carpet versus the chair on a slick floor, or wood, wood on metal, metal on metal. It involves both of the things that are contacting, and it's a complicated question to say exact. We look it up on a table. It's always given to you in the problem, but it is a constant.
But if the weight were doubled on top of it, it wouldn't be 1 for mu sub s. It would still be 0.5.
Yeah, mu sub s would still be 0.5. But you see, if I put the force at an angle, then part of the pushing force would be vertical, part it would be horizontal, and the vertical part would go to increase the normal force, because it would still not be accelerating into the table. Listen, we're going to do lots more of these next week, all right? So what I need to do in the remaining time is talk to you about circular motion. And circular motion doesn't really quite fit with this, right? Because inertial coordinate systems are what? They're related by straight line motion, right? Circle is kind of the exact opposite of that, right? If you, if you take this marker, right, and you make it go in a circle like this, right? And I just take my hand off the marker, is it going to still keep going in the circle? What's going to happen once I let go of this marker? Like that, right? So it does what? It flies off in what direction? The direction tangential to the circle, right? So let me work out some things for circular motion. It's a special case. We've got really nice formulas for it. All right, so Part of the reason I do this is to showcase for you, yet again, the power of the vector method. What is the equation of a circle? If you have a circle, right, and its center is at C, this point right here, which has, let's say, direction C, right? And then we're talking about a circle around that point. So the center of the circle is C, and it's got radius, let's say, R. So here's the motion, trying to draw it. Yeah? So a typical point on the circle might be this point right here, which I'm going to call R vector. All right, and how would you define a circle? It's what? The set of all points the same distance from the center point, right? So a collection of all points equal distance from the center point. That's a circle, yeah? So let's say that distance is R, big R. The formula to define a circle in terms of vectors is just this. The length of the vector, R minus C, is equal to big R. That equation is the vector equation expressing that the displacement from the center to a point on the circle must be equal to the radius of the circle for all points that are on the circle. Now, this equation doesn't give me joy, but if you square it, it's pretty awesome, because then we can express it in terms of dot products. See, this is R minus C dotted with R minus C. And as I derive in the posted notes, calculus works for the dot product just like it works for regular products. There's a product rule. If I differentiate this equation, so let's think about this for a second. I'm thinking about motion, all right? So I'm talking about maybe Bob's at this dot, right? And Bob's going around in a circle. I'm trying to derive things that must be true for the motion of Bob if he's going in a circle, all right? So R is a function of time. C is a constant, right? C, constant. It's the center of the circle. And R is, function of time. Function of time. Differentiate this, what do you get? If I differentiate this, I get dr dt dotted with R minus C plus R minus C dotted with dr dt, because there is a product rule for the dot product. And what's the derivative of R squared with respect to time? R is the radius of the circle, right? It's a constant. The derivative of a constant is 0. But we also know that the dot product is commutative, right? A dot B is B dot A. And what is dr dt? It's v, right? So what this equation says is 2 times the velocity dotted with R minus C is equal to 0. Does that make sense? What is R minus C? Let me make a bigger picture here. What's going on? So we got this circle, right? And here's the center. This vector right here is R minus C, right? R minus C is the vector that connects the center of the circle to the point on the outside. That's R minus C. All right? So R minus C is the radial vector from the center of the circle out to the point. And where is V? Well, it depends on if the circular motion is clockwise or counterclockwise. You guys know what a clock is, right? That starts to not be a joke. So if it's counterclockwise, it should be like this, right? And so there's the velocity vector. What does this equation right here say? This equation says that the velocity, the instantaneous velocity of a particle moving in a circle is perpendicular to the radial vector of that circle. So the velocity has to be tangent to the circle in this sense, right? In the sense of classical geometry, right? What else can we do? How about differentiate again, right? What happens then? we differentiate this again, we get 2 dv. I can drop the 2, right? Let me just drop the 2. So dv dt dot r minus c plus what? Plus v dot ddt of r. What happens when you differentiate r minus c? The c is constant, right? So when I differentiate r minus c, I just get dr dt, because the derivative of c is a constant, which is 0. I mean, derivative of c is 0. What does this say? This says that the acceleration, which is dv dt, right, dotted with r minus c, is equal to minus v dot v, moving the velocity to the other side. So I'll put it up here so you guys can see it better. So what we have is that the acceleration dotted with r minus c is equal to minus v squared, where v is the speed. Now what does this say? Well, if I invent a new notation here, just for the sake of our discussion, let's call a unit vector that looks like this direction here. Let's call this r hat, script r hat, all right? Then this r minus c I can rewrite as r times script r hat, because its length is r. By definition, it's on a circle. And I'm saying that the direction of the radial vector is quote unquote script r hat, just to give it a name. And so what this says is a dot r script r hat is equal to minus v squared, which then says that a dot script r hat is equal to minus v squared over r. In other words, the centripetal, I can't spell, centripetal is equal to v squared over r. The centripetal acceleration is v squared over r. Centripetal means center seeking, which is the opposite direction of the r hat, right? R hat points out. The script r hat points out. Center seeking would be the opposite direction, right? So there it is. So what I'm saying is that it is an inevitable consequence of calculus that if your motion is in a circle, part of the acceleration has to be pointed towards the center of the circle. And how much is pointed towards the center of the circle is completely dictated by the radius of the circle you're going around and the speed. And it has to be v squared over r. These are, that's the only way you can go in a circle. If you're going in a circle, the center seeking acceleration has to be given by v squared over r, independent of the force which is producing that motion, right? So so this is all in my lecture 7, which I will shift over to here now because there's another derivation I want to share with you that I won't write out on the board. I spent too much time on the friction example, and I spent a good amount of time. Yeah, go ahead.
What happened to that 2 you got rid of when you differentiated?
Oh, it's equal to 0, so divide by 2.
Okay. Oh,
Yeah, yeah. Don't worry, it's there if you want it to be. Just put it on both sides. Let's see here. Okay, so all right, so I think I have some pictures for us to look at here. So this is lecture 7. Let me turn the light. You guys won't fall asleep, right? We'll just relax for a second here. So here's the proof of the product rule for the dot product in n dimensions. Hooray! All right. Here's the proof that the dot product is commutative and distributive. All right, there you go. Wonderful. This is not a math class, so I will try not to talk too much about it. I just went through this derivation with you guys. All right. Okay? This is what we just worked out. So I say, okay, well, that's great, but that's not the whole story, right? Because the acceleration of an object going in a circle, it's not just center seeking, right? I mean, it's not. Because there's different kinds of circular motion, right? If you're going at constant speed all the way around the circle, that's different than if you're going around a circle speeding up, right? There's different acceleration involved there. How do we describe that? Well, so here, what I do is I derive the formula for acceleration. So what I do is I'm assuming that something's going in a circle. So I choose coordinates which parameterize the circle as r cosine theta I hat plus r sine theta j hat. This is always possible. It's always possible to view a particle as if it's going along a circle, right? This is part of Calculus 3. We talk about something called the osculating circle in there. For relatively general paths, there always exists an osculating circle. So you can always view part of motion as being infinitesimally along some circle. It's called the osculating circle. And it turns out that the acceleration is always, it never has, the acceleration is always pointed in the direction which is tangent to the infinitesimal plane of motion. Like the acceleration doesn't lift off the infinitesimal plane of motion, as it turns out. This is Calculus 3. So anyway, here, if I take my, hey, my laser. If I take the equations, here we go. If I take this equation, I differentiate. So here, theta is generally a function of time, okay? All right. And I don't know what it is. I'm just leaving it as an arbitrary function of time because I want to describe different kinds of circular motion. Constant rate of change of angle or varying rates of change of angle. Angle. It's all in there. So I differentiate. And when I differentiate, I got the chain rule. I get that. And then I differentiate again. Notice that I've got a product of functions of time. So then I get two product rules, and again chain rules. And then, okay, so then you regroup stuff, and you've got one piece which is proportional to the radius times the change of rate of the angle around the circle squared, with this here. And this is exactly the this is r hat, is what that is. It's the script r hat. It's the outward pointing unit normal to the circle. But there's another piece which is proportional to the radius times the acceleration of the angle, right? The rate of change of the velocity, we call this the angular acceleration. We'll study this towards the end of the course, all right? I'm just mentioning it briefly here, but we later call this alpha. It's the angular acceleration. But anyway, this right here is the tangential direction. So basically there are two pieces. If the rate of change of angle as you're going around the circle is not accelerating, right? If you're just you're just going around the circle at a constant rate of angular development, so that would end up meaning that you have constant speed. If you're going around the circle at constant speed, it turns out that this term is 0 and you just have the centripetal acceleration. So the centripetal acceleration is the net acceleration only in the case that the speed is 0. So here's some pictures that are helpful, I think. This derivation up here, what I just worked out, is that the acceleration has two pieces. It has the centripetal acceleration, and there should be a minus there, my bad, because the normal I just said was the outward pointing normal, I think. Well, the picture is right. Like the centripetal acceleration should be center seeking, okay? So, right. I think I maybe should have a minus right here, but and then there's the tangential acceleration, which is given by r d squared theta dt squared. Now, since the arc length is the radius times the angle in radians, if you differentiate this, you get ds dt is r d theta dt. So ds dt is the speed, and d theta dt we sometimes call omega. It's the angular velocity, as it's called. But anyway, these are just words for us until later. You don't have homework problems on it. What you do have homework problems on is circular motion, all right? But all you need to know, really, is that the net acceleration, it's v squared over r plus this piece over here, the tangential acceleration, all right? So, and this could be rewritten as, where is it? Well, all right. let me just take a breath here. Any questions? Yeah.
You said that centripetal acceleration should be negative v squared over r.
It should be, in terms of the direction vector n, I think, as I've defined it up there, it's an outward pointing unit normal. So since n is outward pointing, it needs to be minus because it's the centripetal is center seeking. Listen, another thing to notice here, these are perpendicular vectors. The normal and the tangential directions are perpendicular. So what's the magnitude of the acceleration? It's the square root of v squared over r, quantity squared, plus the tangential acceleration squared. So you might have a problem where you have both, and then just remember these are perpendicular, so it's essentially like x and y in terms of the magnitude. So let's actually run some numbers. All right. So one thing that flat earthers often criticize, us globular people or whatever, is this idea that the Earth is spinning. It's a ball spinning in space. And if that's the case, why don't people on the equator just go flying off? Right? It's spinning. So why don't the people on the equator fly off? Well, the question is, what is the acceleration due to that motion around the axis of the Earth, right? In context, how does that square up against gravity, right? The force of gravity gives us an acceleration of 9.8 meters per second squared, right? So if you imagine you're on the equator of the Earth and you're going around the axis like that, right? Well, there has to be some sort of, force keeping you from flying off, right? It's gravity is what it is. How much of gravity is used to keep you from flying off the equator due to the circular motion around the axis? Not much. Here's the details. So the radius of the Earth, I think it's about 6,371 kilometers. So you can figure out the speed. It's the circumference of the Earth, and how long does it take for the circumference? How long does it take to a point on the Earth to go all the way around its axis? This is what we call a day, yes, or yom in the Hebrew, I've been told. But where was my answers in Genesis person? But no, that might come up. I don't know. But okay, so anyway, there's 86,000. Oh man, I forgot the number. 86 some odd thousand seconds in a day. 24 times 3,600, and so there you go. It's moving. The velocity of a point on at the equatorial region with respect to the axis of the Earth, it is moving 463.3 meters per second, 1,000 miles per hour. I mean, hey, they're not wrong. It's fast. But what kind of centripetal acceleration are we talking about? V squared over the radius of the Earth. The thing is, that is this. So the centripetal acceleration, right, for a point on the equator is something like 0.034. So is that measurable? Sure. Yeah. In fact, the force of gravity is a little bit lower at the center of on the equatorial region, as opposed to like up at the poles. And that's part of why the Earth is not a sphere. It's an oblate spheroid, because it does spin out a bit. Okay. What about the other celestial motion? What's the centripetal acceleration of the Earth relative to the Sun? So 2 pi radius of the orbit divided by 365 times 86,400. So this is the number of seconds in a year, ignoring leap years. And that works out to, whoa, we're really moving around the Sun. Look at that. Our tangential velocity with respect to the Sun, Earth's orbital motion about the Sun, and the galactic plane motion, solar plane motion, almost 30,000 meters per second. Yowzers. And yet, but the distance is so far, right, that the centripetal acceleration of the Earth around the Sun is still just 0.00595 meters per second squared. So, there's two things going on, the v squared and the r. When r is super big, v can also be big, and the centripetal acceleration is still small. Yep.
How do you reconcile those two numbers? What effect does it have?
I do think they have, what is the difference between, how do you feel I'm not sure what your question is. Oh, how would you feel both of them at the same time?
No, I mean, like, what would that, like, in terms of, like, how much accelerated?
Well, it's complicated, right? Because it's so the centripetal acceleration of the Earth spinning around its axis, it's center seeking for the Earth. But the centripetal acceleration with respect to the sun, it's always like pointing towards the sun. So they're not exactly related. They're like they're different directions, different times. It's complicated. I mean, the long and short of it is actually very complicated to completely describe all of the how force of gravity works between the Earth and the planet, the sun and the planets all together, because you also have to account for the planet, like the tug of the planets on the planets. I mean, this is actually very complicated, and it took mathematicians the better part of decades in the 19th century to like work it out to a degree of accuracy people were comfortable with. More about that later, though. I'll come talk to you in just a second. Have a good weekend, guys.